Good morning, class. So this is the first of two screencasts on deadlocks. Today we'll focus on these three topics, and here are the two chapter objectives. So here's the system model. We have a system consisting of some number of resources. Classically, I/O devices are used, so things such as in older systems, tape drives, printers, things of that nature. So the resource types you can see there are R sub 1 through R sub M, and we're assuming that we have W sub 1 through W sub N instances of each resource type, and we assume that the way a process uses a resource is to request it, use it, and then release it. And a process can hold several instances of resources of various types. All right, so all four of these conditions have to hold simultaneously for a deadlock to exist. These are necessary, but not necessarily sufficient conditions. So mutual exclusion, we assume that only one process at a time can use a resource. Hold and wait, which says that a process is allowed to hold resources while requesting additional resources. No preemption, that says that the operating system can't take away resources being held by a process from that process. It's a preemption that prevents deadlocks on CPU cycles or memory allocation, right? Because the kernel can certainly preempt a process that's hogging CPU cycles or hogging up too much memory. And finally, circular wait, which when we look at resource graphs a couple of slides later, you'll see that in the resource graph, if we can identify a cycle, that might imply a deadlock. Okay, we can have mutex locks and semaphores can be thought of resources, right? Think about one of the potential solutions to the dining philosopher problem, the one that has all of the philosophers first picking up the left chopstick and then trying to pick up the right chopstick. So that meets the four conditions for a deadlock right there, right? Mutual exclusion. Only one process can use a chopstick at a time. Hold and wait. Each process is holding its left chopstick and waiting for the right chopstick. No preemption. There's no actor in that story that takes chopsticks away, and circular wait. Right now, you can picture the cycle that we have among the philosophers. So remember that one of the solutions to that problem is to have one philosopher, rather than requesting the left chopstick first and then the right, actually request the right chopstick followed by the left chopstick, and that prevents the circular wait from forming. Okay, so now we come to the resource allocation graph, and remember, being computer scientists, a graph isn't an illustration of a curve, like I saw some of you use for the process state graph on the first exam, but it's a set of vertices and a set of edges, right? The way that computer scientists think of graphs. So we have two types of vertices, one representing processes and the second representing resources, and the resource vertices will show the instances, the number of each type of resource, and then two types of edges. A request edge, which goes this directed edge from a process vertex to a resource vertex, and an assignment edge, which is a directed edge from a resource vertex to a process vertex. All right, so here's an actual illustration of the vertex types and the edge type. So our process is represented by a circular vertex. A resource with 4 instances is shown as a square vertex with the resources shown within the vertex. And as noted earlier, a request edge is a directed edge from a process to a resource, and an assignment edge is a directed vertex from a resource to a process. So here's an example. In this example, process 1 is holding one instance of resource 2. It's requesting an instance of resource R sub 1. You can see that process 2 is holding an instance of R sub 1 and an instance of R sub 2 and requesting an instance of R sub 3. And finally, process 3 is holding an instance of R sub 3. So here's an example of a resource allocation graph illustrating a deadlock. We have this cycle in the graph here, but this cycle isn't, in a sense, the one illustrating the deadlock, because if it were the case that process 1 could release this resource, then process 3 could pick it up, and that would break this cycle. But notice that we actually have a cycle that goes like this, and that involves all of the processes. So that's the actual cycle illustrating the deadlock, right? Because every process is holding and waiting, and there's no possibility of a resource being released to break the deadlock. So here's an example of a resource allocation graph with a cycle. There's the cycle, but no deadlock at the moment. If P2 releases this resource, then this request can be satisfied, and that breaks the cycle. Or if P4 releases this resource, then P3 can take it, which will break the cycle. But of course, if P2's next action is to request another instance of either resource, and P4 does the same thing, then we will have a deadlock. All right, so from those couple of examples, this is what we can conclude. If a graph contains no cycles, there is no deadlock. If a graph contains a cycle and there's only one instance per resource type, then we do have a deadlock. Because if there's no additional instance that can be returned by another process, that would break the circular wait, which is the second sub-bullet point there. If there are several instances per resource type, we might be in deadlock or we might not, right? It depends upon the details of the resource allocation graph. All right, so there are 3 basic strategies for handling deadlocks. First, ensure that the system never enters a deadlock state by using deadlock prevention and deadlock avoidance, which we'll take a look at next time. The second strategy is to allow the system to enter a deadlock state and then go in and recover by removing one of the 4 conditions, or thirdly, just sweep the problem under the rug, which is, as noted here, an approach taken by several actual operating systems. So that completes this introductory material. See you next time.